From string theory to observations, the multiverse theory is far from safe. A common science fiction trope, the concept of a multiverse made up of parallel universes, was recently examined in the Oscar-winning film Everything Everywhere All at Once. It is, however, conceivable from a science perspective. It is critical to note right away that our current knowledge of the basic laws of physics determines whether or not the multiverse exists. It was not created by irrational physicists who read too many science fiction novels. The universe exists in various forms. The universe of atoms and particles is governed by quantum mechanics, which provides the basis for the first and possibly most well-known version. It implies that a particle can exist in a variety of states simultaneously, until we measure the system, at which point it chooses one. One interpretation holds that all quantum possibilities that we weren't able to observe are actualized in other worlds. The cosmological multiverse, the second form, results from cosmic inflation. The physicist Alan Guth proposed in 1981 that the early universe experienced a period of accelerated expansion in order to explain why the universe today looks fairly uniform throughout. Space was stretched during this inflationary era to the point where any 2 points were pushed apart faster than the speed of light. The existence of the primordial seeds that eventually gave rise to cosmological structures like stars and galaxies was also foretold by the inflationary theory. By observing minute temperature variations in the cosmic microwave background, or the light remaining from the Big Bang, this was successfully discovered in 2003. Then, it was measured by the space experiments WMAP and Planck with unmatched accuracy. The majority of cosmologists now view cosmic inflation as the de facto explanation of the early universe as a result of its remarkable success. But cosmic inflation had a, possibly unintentional, side effect. Inflation involves the stretching and smoothing of space on scales that are typically much larger than the observable cosmos. Even so, cosmic inflation must eventually come to a stop in order for our universe to be able to develop into what it is today. But it didn't take long for scientists to realize that if inflation were actually real, some parts of space-time would continue to expand even as it stopped doing so in other parts. It is possible to think of the areas that keep expanding as a distinct universe. A multiverse of universes is created as a result of this process, which never ends and results in expanding universes generating even more expanding universes. Eternal inflation is the name given to this occurrence. In the early 21st century, eternal inflation, first proposed by physicists Paul Steinhardt and Alex Vilenkin in 1983, was combined with a concept from string theory to create a contentious but convincing explanation of why our current physical laws exist. String theory, which unites quantum physics and gravity, is currently our best hope for a theory of everything, though it has not yet been proven. However, string theories that are scientifically plausible need to have 10 or more dimensions, rather than our normal 3 spatial dimensions plus time. Therefore, 6 or more of these dimensions must be compactified, curled up so that we can't see them, in order to characterize our current universe. This can be mathematically modeled in a known way. The issue, or feature, depending on your perspective, with this process is that there are at least 10,500 different methods to compactify data. This staggeringly expansive array of options is known as the string landscape. A different collection of physical laws, possibly corresponding to a different universe, will result from each compactification. 2 important issues arise as a result. Where are we in the string landscape, and why? The first issue has an elegant solution thanks to eternal inflation. Because every expanding universe in the multiverse realizes a distinct point in the string landscape, the multiverse can contain every possible combination of physical laws. Nevertheless, why does our universe do such a fantastic job of producing intelligent life like us? According to statistics, some universes should resemble ours since we inhabit the universe where our physical laws are what we can witness. This opinion, however, has generated a lot of debate because many contend that it is not grounded in science. The observability of the universe is clearly a problem. Is it then even theoretically feasible to observe the other universes, assuming it does exist? No, distinct universes do not communicate in the quantum multiverse. But if we're fortunate, the answer is yes, in the inflationary multiverse. Since the various universes share the same physical space, it is theoretically possible for neighboring universes to clash, potentially leaving remnants and imprints in our observable universe. Although these signatures have not yet been discovered, a research collaboration led by Hiranya Piris of University College London and Matthew Johnson of the Perimeter Institute demonstrated that such collisions should in fact leave traces on the cosmic microwave background, light left over from the Big Bang, that can be searched for. The next difficulty is conceptual. Many of the universes in the string landscape, according to some theorists, are essentially mathematically impossible to exist in the same way that our universe does. They do, however, exist in a swampland of solutions, and it appears to be challenging to discover string theory solutions that allow for cosmic inflation. On whether string theory can, even in theory, explain inflation, cosmologists and string theorists are in sharp disagreement. This conundrum is both frustrating and intriguing because it implies that one of the two theories is incorrect, and that either one will cause a change in theoretical physics. Lastly, the very foundation of cosmic inflation is currently under scrutiny. The purpose of cosmic inflation is to dynamically transform the cosmos into the uniform universe we see today, independent of how the early universe appeared. However, the question of whether cosmic inflation can truly start in the first place has never been thoroughly studied. This is due to the fact that the equations defining the start of the process are too challenging for analytical solutions. However, a number of study teams around the globe, including my own at King's College London, are currently putting this theory through a rigorous testing process in an effort to solve these formerly intractable equations. Watch this area, then.